In this video, we'll see a necessary condition for Hamiltonian graphs. We'll use the contrapositive of this theorem to prove that a graph is not Hamiltonian. We'll see that this is not a sufficient condition to be Hamiltonian with an example. And finally, we'll take a look at a proof of the theorem in question. So we've seen so far lots of or several sufficient conditions for Hamiltonian, right? If a graph has a certain property, for example, the degree sum, the non-adjacent degree sum condition, the minimum degree condition, we can show that the graph is Hamiltonian. So what we're looking at here are necessary conditions. That is, if a graph is known to be Hamiltonian, then what do we know about the graph? And so in particular, we look at this condition given by theorem 6.11 that says if a graph is Hamiltonian, then the number of components in G minus S is at most the cardinality of S, where S is any non-empty proper subset S of V of G. So remember this K of some graph is the number of components. So this is not kappa, this is not connectivity. Number of components of G minus S. So what we're saying here is take any non-empty proper subset of vertices, call it S, remove it from the graph, count the number of components, and compare that to how many vertices you removed from the graph. In particular, if the number of components left over after removing those S vertices is more than the number of vertices you left over, we can conclude that the graph is not Hamiltonian. That is, I just stated the contrapositive of theorem 6.11. Right? Let G be a graph. Suppose there exists some non-empty proper subset of its vertices such that the number of components in G minus S is strictly bigger than the cardinality of S, then G is not Hamiltonian. So this is a pretty nice theorem. Let's see how to apply it. So let's take a look at this graph. Claim that this is not Hamiltonian, and let's see why. So what we can do here is scan for vertex cuts of the graph. Some of these might work, some might not. So yeah, let's see. For example, I could remove, let's see. I could remove U and X. U and X is a vertex cut of the graph, right? But that would leave, let's see, how many components would be left over if I removed U and I removed X from the graph. That would leave V in a component by itself, and the rest of the vertices would be in a component by itself there. So there, the number of components in the resulting graph after removing the vertices would be 2, and the number of vertices I removed was 2. So that wouldn't show that the graph is not Hamiltonian. So that's not a good cut set or vertex cut for our purposes. So we keep scanning for vertex cuts, and if you find one that separates it into more components than you took away, then you're good. So for example, W and X. If I remove these two vertices, then my components would be just S and T, this K2, this K2 with U and V, and then this K2 with Y and Z, right? The resulting graph G, if this is my graph G, then G minus WX would be the graph ST, UV, YZ would be the graph left over. And so the number of components there is 3, right? Number of components in G minus S, let's say S is WX, would be 2, but the cardinality of S, this would be 3, but cardinality of S is 2. And so there we see number of components left over is greater than the number of vertices that I removed. And this implies, so together, here we have S strictly less than the number of components in G minus S. And so that implies that G is not Hamiltonian. So that's the idea, is to find a subset like this. Okay, let's, right, so one point I should mention here is that this is not, right, it's a sufficient condition for being not Hamiltonian, but it's not necessary for being not Hamiltonian. That is, just because a graph is not Hamiltonian doesn't mean you'll be able to find such a set of vertices. Right? That wouldn't, just because we can't find that set of vertices does not mean G is Hamiltonian. So in particular, what I'm saying here is that this necessary condition for being Hamiltonian, that this is true for every subset, that's not sufficient. This can be true, and the graph can still be not Hamiltonian. So, for example, is the Peterson graph. Of course, one can check, and in fact, I'll prove this in the next video, that the removal of any set of vertices, right, if you remove any set S of vertices, any vertex cut, that the number of vertices you removed is at least as big as the number of components that are left over. Yet, the Peterson graph, as we know, is not Hamiltonian. So, while it can show a graph is not Hamiltonian, it can't show a graph is Hamiltonian just by showing that no vertex cut works. Right, again, this is the difficulty with Hamiltonicity, is we don't have a necessary and sufficient condition. All right, well, let's take a look at a proof of this theorem. The idea is simple enough, so I'm going to do, let's say proof here. First, let's get it out of the way. So let S be a set of vertices, a non-empty proper subset of vertices. Non-empty proper subset of the vertex set of my graph. Right, let G be a graph. So first off, if S is not a cut set, if it's not a vertex cut, that is, if G minus S is connected, well, then the number of components in G minus S is equal to 1, and that's certainly less than or equal to my non-empty set of vertices. So we might as well assume, right, that this has no chance of working, so we might as well assume, that the number of components in G minus S is some integer k, and that's at least 2. Okay. And let G1, G2, up through Gk be the components. Of G minus S. And then let's get our cycle. We know the graph is Hamiltonian. Since G is Hamiltonian, let's see, and we'll call this here V1, V2, up through Vn, back to V1, be a Hamiltonian cycle. And we might as well assume, right, so it's okay to assume we can label this differently if it's not the case. We can assume that V1 is in the first component of the graph. Okay, so here's the idea. I'll put my Hamilton cycle up here, V1 to V3. And let me just do this with an example with, let's say, 10 vertices. So this is V1, V2, V3, V4, V5. Because the notation for this proof can get a little bit tricky unless you're very comfortable working with subsequences. So this is V10, not V16. So here's my Hamiltonian cycle. There could be, again, other edges in here. So we're thinking of sort of worst case scenario. Sort of take away all the other edges of the graph except for the Hamilton cycle. And we've removed some set of vertices and left a disconnected graph, right? G minus S is disconnected. And for the sake of, just as an example, let's say we remove V3 and V7 and V9. Let's suppose those were the vertices that were removed. So this set here, this is the one that V1 is in, and so we're calling this G1. And so that means, we'll call this one G2, right? These would be a component by themselves after we remove these vertices. G1, G2, and G3 would be my components left over. Right, how do I make this clear? The idea is I want to say something about how many vertices I must have had to remove, right? We're just letting S be some set of vertices. I want to count the vertices that are in S that left these 3 components, for example. So the idea is I make a subsequence of the cycle. And so I'm going to let Vij be the last vertex on C that belongs to Gj. And I'm going to do that in general, but for this example, what does that look like? This means that Vi1, this is the last vertex of the cycle that is in G sub 1. That would be V2. So V sub ij, that's V2, and maybe I'll just say over here, that means I1, that index is, that looks like a J, sorry, maybe that's confusing. Let me do it just a colon. I1 is 2. V sub I2 to be the last vertex on the cycle that belongs to G sub 2, that's V6. So I2 is equal to 6. And then finally, V sub I3, I only have 3 components here, but in general, we can keep doing this. Just let V sub ij be the last vertex on in that component that's on the cycle. This would be V sub 8. So here I can say I3 is equal to 8. So, okay, so how does this labeling scheme help me? How does this subsequence help me? Well, it helps me identify what the vertex cut was, right? If I know that V sub I1 was the last vertex on the cycle in G sub 1, that means that the next vertex, that is V sub I1 plus 1, that would be V sub 3 in this case, is in my set. It had to have been removed, otherwise this wouldn't have been the last vertex in this component. And so in general, then V sub ij plus 1 is in S for each, I did this for each component, so this is for each j between 1 and k. Right? Again, you can check I sub 2 was 6, so V sub 7 I'm claiming would be a cut vertex. Yep, it was here. Same with V sub 9, that was a cut vertex, and these are all the cut vertices. And so if I know that at least this many vertices, 1 for each component, is in the vertex cut, then I can say cardinality of the vertex cut is at least k. And remember, that was the number of components in G minus S. And so that's the result that we wanted, right? Number of components is at most the number of vertices that we removed from the graph. And that's a proof. Okay, that's it for this video. In the next video, we will, so taking into consideration this example I showed you down here with the Peterson graph, tell a story of an attempt to find a necessary and sufficient condition that does involve this. All right, so I'll see you there.